Today's topic is inverse probability weighting, or IPW. Let's explore how to uncover the true cause using only observational data. Let's look at an example. If you take a cold medicine and recover in a few days, you naturally think it was thanks to the medicine. But was it really because of the medicine? Today, we'll talk about how to tell whether a difference we see is truly caused by that factor. It does feel obvious that taking medicine helps you recover faster. And checking it seems simple. We just compare the recovery time of people who took the medicine with those who didn't. Let's look at data from one hospital. People who took the medicine recovered in 5.6 days on average, but people who didn't take it recovered in just 4.7 days. So the group that took the medicine was actually sick 0.9 days longer. At this rate, the medicine looks harmful. But is that really true? This is exactly where the trap is. This time, let's split the patients into severe and mild cases. First, the severe patients. With the medicine, recovery took 7 days on average. Without it, 8 days. So the medicine sped up recovery by 1 day. What about the mild patients? With the medicine, recovery took 2 days. Without it, 3 days. Here too, the medicine cut recovery by a day. Isn't that strange? In both severe and mild cases, the medicine clearly sped up recovery. But when we combine them and look at the whole, the result flips, and the medicine looks harmful instead. Why on earth does this happen? To solve this puzzle today, we'll explore IPW. Let's revisit the problem we just saw. In both severe and mild patients, the medicine clearly sped up recovery by 1 day each. But looking at the whole, the group that took the medicine actually takes 0.9 days longer to recover. The effect is completely reversed. When we split the data, the medicine clearly helps, but when we combine it, the medicine looks worse. This phenomenon is called Simpson's paradox. So why does this happen? Let's take a look at the makeup of each group. The group that took the medicine was originally packed with severe patients who recover slowly. On the other hand, the group that didn't take it had many mild patients who recover quickly. From the start, the makeup of the two groups was completely different. So the group that took the medicine looked slower to recover overall, and the medicine appeared harmful, flipping the result. A variable that affects both whether you take the medicine and your recovery time is called a confounder. In other words, being severe or mild is the confounder here. So what should we do? The key idea is simple. We imagine what it would look like if the two groups had the same ratio of severe and mild patients from the start. We don't change the data itself. Instead, we give each person a weight. First, let's find each patient's probability of taking the medicine. Let's mark each patient with a circle and color in only those who took the medicine. Among the 6 severe patients, 5 took the medicine. So the probability that a severe person takes it is 5 out of 6, about 83%. Among the mild patients, 2 of 4 took it, so that probability is 2 out of 4. That is 50%. Now we use the reciprocal of this probability as the weight. Common cases get a small weight, and rare cases get a large weight. For example, a severe person who took the medicine gets 1.2 times, while one who didn't take it gets 6 times the weight. For mild patients, the two sides are similar, so we multiply both by 2. Once we apply these weights, the ratio of severe to mild becomes the same in both groups. A rare person with a large weight comes to represent several people, while a common person with a small weight has less influence. Then, as if the patients had been fairly divided from the start, the data becomes balanced. This method is called inverse probability weighting, or IPW. Now we just compare the averages again on the balanced data. We multiply each person's recovery days by their weight, add them all up, and divide by the sum of the weights. Doing this, the weighted average for the group that took the medicine is 5 days, and the weighted average for the group that didn't take it is 6 days. Now the group that took the medicine recovers 1 day faster. The medicine that looked harmful was actually speeding up recovery by a day. Only after removing the effect of severe and mild does the medicine's true hidden effect appear. In this way, IPW reweights the data as if the medicine had been randomly assigned from the start. Now we can compare the data in a balanced way, just like a randomized experiment. Now let's generalize what we just did with a formula. Let's check just a few symbols together. T indicates whether the medicine was taken, 1 if taken, 0 if not. X represents the patient's state, that is whether they are severe or mild. And we'll write the probability that a person in state X takes the medicine as follows. Now let's define the weight. We give the reciprocal of the probability of the event that actually happened. For a person who took the medicine, we give the reciprocal of the probability of taking it. For a person who didn't take it, we give the reciprocal of the probability of not taking it, that is 1 minus the probability of taking it. The rarer the event, the smaller its probability, so its reciprocal, the weight, becomes larger. Shall we combine these two cases into a single formula? The left term is for people who took the medicine, and the right term is for people who didn't. If t is 1, only the left term remains. If t is 0, only the right term remains. This way, each person is given exactly one weight that fits their own case. Until now, we could count the probabilities by hand because there were only two cases, severe and mild. But here a problem arises. In reality, there's much more to consider: sex, age, weight, even pre-existing conditions. When there are this many confounders, counting probabilities one by hand becomes impractical. So we change our approach. The probability that a person takes the medicine, given their information. This is called the propensity score. It's just a name for the same probability we used before. So how do we find this probability? We train a statistical model on the data to estimate it. A common method is logistic regression. When we feed in patient information like sex and symptoms, a curve called the sigmoid squeezes the value to between 0 and 1. This curve sticks close to 0 when the input is very small and approaches 1 when the input is very large. So no matter what information comes in, the output is always between 0 and 1, in other words, a probability. The probability the model estimates this way is called the estimated propensity score. Once we have the estimated propensity score, the rest is the same. Just as we learned, we make the weights from the reciprocal of the score. But there's one thing to watch out for. All of this only holds when the propensity score is estimated well. For example, imagine a formula with only sex and symptoms. Suppose age strongly affects whether someone takes the medicine, but the model has no variable for age. In that case, we miss the real effect of age on taking the medicine. As a result, the estimated probability differs from reality, and the confounding isn't cleanly removed. So in real analysis, which information you put into the model matters more than anything. Let's wrap up what we've learned. We wanted to know whether the medicine really speeds up recovery, but we couldn't just compare those who took the medicine with those who didn't, because the group that took it was crowded with severe patients and the group that didn't with mild patients. When the two groups start from different baselines like this, the confounder hides the true effect. What solved this problem was IPW. By giving each person a weight equal to the reciprocal of the probability, we make the makeup of the two groups the same. Then the medicine that looked harmful revealed its true effect, speeding up recovery by 1 day. In real data with many variables, we estimate this probability with a model like logistic regression. The probability estimated this way is the estimated propensity score. Using this estimated propensity score, we assign a weight to each individual. Then overall, we can make the makeup of the two groups the same. Of course, if the model is inaccurate, IPW wavers too, so we must be careful about what information we include. The greatest appeal of IPW is that even when experiments are hard, it can estimate causal effects from observational data alone. If there are confounders we couldn't measure, its limits are clear, but used carefully, knowing those limits, IPW gives answers that a simple average comparison never could.